This lesson covers operations with complex numbers. Specifically, addition and subtraction. We'll handle multiplication and division in Part B. We'll also look at graphing complex numbers on the complex coordinate plane. Now, in the past, we have encountered complex numbers, say like 3 plus I square root of 5 on 7, and I said that when you get into analysis or calculus, that's a sufficient presentation of the answer, but for our purposes, I've emphasized distributing that 7 from the denominator as a 1/7 to each term in the numerator so that I was always out to the right unless you had a number like 2 plus square root of 3i. We don't want the I to be all the way to the right because it could look like it's part of the radicand. So instead, the convention is to write it as a coefficient. Something like that. Now, the reason why is because this is going to be the A value, or the horizontal dimension on the complex coordinate plane, and this is going to be the B value, which is going to be the real number part of the imaginary number, the vertical component of the point on the complex coordinate plane. And when we rewrite it like this, all of that is very clear. We don't have to digest it from an unsimplified form. So you can graph complex numbers, and you have to make sure to understand that the vertical axis represents the imaginary numbers. And so that's why I need you to clearly label your vertical axis with the I to represent imaginary numbers, and then represent the horizontal axis using the blackboard bold symbol for the set of reals. So I'm going to color code these, graphing each complex number. I first take the real part, go in that direction 2 to the right, and then the imaginary part, that tells me, the I tells me that is going down 3. So I go right 2, down 3 for A being in the 4th quadrant on the complex coordinate plane. For negative I simply just go down 1. For 4 plus 0i, that's really just a 4, so I go to the right 4. And then for part D, that's going to be negative 2 plus I. So 2nd quadrant. So just remember that the vertical axis represents the set of imaginary numbers. The horizontal axis is now the set of reals. And then a complex number, we break it into 2 parts, so then it has 2 dimensions. So continuing with this idea that a complex number is graphable, we want to say that the absolute value of a real number gives the distance of that complex number from the origin on the complex coordinate plane. And to take a look at this as using an example, let's say we had, I'll just go right to the first example, and then I'll explain where this comes from. It's the Pythagorean theorem, so a squared plus b squared equals c squared, but we take the square root of both sides so that we get just the length of the hypotenuse. And remember, that comes from right triangle trigonometry, where this side length would be A, this side length would be B, this side length would be C. And then if we want the distance between these 2 points from the origin to this point, then we want the value of C. So harking back to geometry. So in this example, I'm going to plot this on the complex coordinate plane, which you don't have to do. I'm just using this as a visual to show you where the formula is coming from. And then I plot the 3, so that's 3 to the right, and then the 5. Puts us up 5, so right 3, up 5. So that's where that complex number would be graphed on the complex coordinate plane. Now that creates a right triangle with a horizontal distance of 3 and a vertical distance of 5. And so then if this is the hypotenuse, that's also the distance. Remember, Pythagorean theorem is really just the distance formula when applied to a coordinate plane. So that's why, I'd have c squared is equal to 5 squared plus 3 squared, or just the distance of this number from the origin, the hypotenuse length, is the square root of that. So be very careful here and do not distribute the square root to the radicand because of this addition that's not allowed. So just simplify the radicand as far as it could go. So 5 squared is 25, and then you have 3 squared, which is 9. And again, do not take the square root even though you see two perfect squares. The sum of 25 and 9 is 34. It has a pair of factors of 17 and 2, neither of which are perfect squares, so that will be the full simplified answer. And so that's about 6. It's like 5 point something, so that would be the magnitude or the length of that vector here. And a vector is something that has both magnitude and direction. So if you kick a soccer ball, how hard is the magnitude, and where or to whom is the direction? Looking at the next example, I could rewrite this so that it is in the complex number form where the b is just 0. And then when you substitute it into the formula, you'll kind of see that really I'm going to get back just 13 because 0 squared isn't going to produce anything significant. And the negative is squared, so now that's just positive 169, which is the perfect square of 13. So I showed all the work there, but you could just simply say, hey, if one of the parameters, a or b, is missing, you could just take the positive of the number. And that's what we should realize. The absolute value of negative 13 is 13 because the distance of negative 13 from 0 is 13. And in the next example, again, I'll show all my work. The parameter a here is 0 because it's not written. And then I have the square root of the sum of the parameters, so 0 squared, and then that's going to be plus the quantity of negative 7 squared. So that negative is squared. So that makes it positive. So it's 0 plus 49, or the square root of 49, which is just 7. As you can see, it's just the positive of the b parameter, which is the real part of the imaginary part of this complex number. Do not let the simplicity of these problems fool you. You may want to keep the graph of what's going on behind the scenes in the forefront of your mind, because these are one of those problems when you get to the test, it's easy to blank because it's not something like x squared is equal to 9, where the algebra, the symbols in front of you remind you what to do. So moving on to the last page, now we'll add and subtract complex numbers. To analogize, we could think about, say, 3x squared plus 4 is equal to, or let me say, this quadratic binomial, and let's say minus x squared minus 2. So the parentheses just group here, so they don't mean multiply because we have a subtraction between each pair. So instead, I will take that negative and distribute it because I'm subtracting every term to the right, and then I'll remove the parentheses on the left, changing the signs of every term to the right of the subtraction, and now I'll combine like terms. So I have, these are like, so that means they have the same variables to the same exponents. They both have x squareds, so then you operate on coefficients. 3 minus 1 gives me 2x squareds left. And then I have plus 4 and plus 2. Those have no variables to no exponents, so they're like terms. 4 and 2 make 6. So with complex numbers, it's similar. So again, we're adding, so that means the parentheses are just grouping. This is a single complex number added to another complex number. So I take the like parts. 4 plus negative 6 is equal to negative 2. and then I take the imaginary parts. 2i plus negative 7i is negative 5i. And that is the sum of those two complex numbers. And then in the next example, here we have a negative that I want to distribute. So I'll change the signs of every term to the right, and then combine like terms. 2, the real part is by itself, and I always want to write that first, so it's in the form a plus bi, the standard form for complex numbers. That gives me 2 plus 2i, which I don't need to factor. I know they share a common factor of 2, but this isn't like 2 plus 2x, which would equal 2 times 1 plus x. This is not a factoring problem. This is writing complex numbers in standard form, if you will. So there is something in physics called the parallelogram rule. You do not need to execute this in this course, but it is neat to connect these two subjects, and it is used for adding vectors. Again, that's like from Despicable Me, the villain, he says he has both magnitude and direction. So basically, if I were to graph these two complex numbers in our example that we're going to add together, it's going to mimic this idea of, say, me in a kayak rowing from one side of the Delaware to the other, and so I'm paddling at a certain speed, but I don't end up going straight across the river from where I put in my boat. But instead, the current takes me downstream because it has its force and I apply my force. And so that's the idea of adding two vectors together. Let's take a look. So this is going to use geometry in order to add complex numbers. So we're tying together different maths. So I'll let the first complex number be represented in red, and remember to label your axes because it's unconventional that it's going to be the set of reals and the set of imaginary numbers for horizontal and vertical respectively. So write 3 down 1. Now that creates a point, and then it is a vector from the origin. So think of a vector as a ray that has a terminating point. That's like how far the soccer ball would go if you kicked it with a certain amount of effort. And then in blue, I'll label the other complex number going right 2 up 3. Now, you'll probably get the gist that the answer should be somewhere over here if you were to fuse those two vectors together. And the way that you do this is now I'm going to find the slope of the first complex number, so it's down -1 and it's right +3. So then its slope is going to be m of -1/3. And then that means I pick up from the other vector's endpoint, I go down 1 and then right 3 and plot a point, and I'm making a parallelogram because now the two red vectors have the same slope. And I do the same thing with the other vector, the blue one. It rises 3 and it runs 2, so it has a slope of 3 on 2. So then I go where the other vector left off. I go up 3, 1, 2, 3, and then right 2. And then I arrive at the same place where the other vector left off, creating a parallelogram, which is a closed figure or a special type of polygon where pairs of opposite sides are parallel. And so now this result, which I'll label in purple because that's the color of blue and red mixed, that is going to be the geometric result of this addition here. I just used a different type of math to come up with the answer. So I have 1, 2, 3, 4, 5 to the right, and then 1, 2 up. And if we take a quick look, it would be 3 plus 2, that would equal 5, and then -1 plus 3i would equal 2i. So we are able to confirm the two types of math that we used.